Hello, everyone. My name is Arthur. I'm a compiler engineer at Azul, where I work on Falcon compiler. Falcon is a just-in-time compiler for Java based on EuroLLVM. And in this session today, I'm going to be talking about inlining in Falcon and how it is different from inlining in EuroLLVM upstream. Falcon compiles from Java bytecode into native code. It does it inside of a running JVM, and then we execute the compiled code straight away. Falcon is the final tier compiler in Azul's prime JVM. It means that Falcon compiles only a small fraction of all methods being executed by the VM. But these are the hottest methods, so the quality of optimizations really matter for the overall performance of the system. If you want to learn more about Falcon, here are some other talks we've presented over the years, explaining various technical aspects of our compiler. Inlining is a simple compiler transformation. It is a replacement of a function call side, with the body of the function being called. This transformation has both positive and negative effects. On the positive side, it obviously eliminates the call overhead. But more importantly, it enables other optimizations. It does it in two ways. First, it facilitates information flow by removing the call boundary. Imagine the called function returned a constant. After inlining, this constant becomes available in the caller function and can participate in other optimizations, like in constant foldings. And second, inlining creates a specialized copy of the called function specifically for the inline call side. We can optimize the specialized copy more aggressively. On the negative side, inlining increases the size of IR. Because we need to pull more code through the optimizer, it increases compile time. Increased IR size can also hurt the quality of optimizations. We have different limits and cutoffs in various places of EuroLLVM, where we limit the amount of work we do for compile time reasons. For example, some paths can look only at a limited number of blocks in order to find some particular fact. And with larger IR size, we can hit these limits and cutoffs more often. Increased IR size translates into increased code size. And this alone can hurt performance. We can start experiencing more instruction cache misses, for example. Balancing these two kinds of effects is critically important for performance. And the rest of the talk is going to be about how we built an inliner that tries to make this balanced choice right. Now let's see how EuroLLVM solves this challenge. There are several inliners in EuroLLVM, but I will only be talking about general-purpose inliners. The default inliner in standard pipelines is the bottom-up inliner. It operates on the graph of strongly connected components of the call graph. If we look at an arbitrary call graph, there might be cycles due to recursion. But if we isolate cycles into strongly connected components, the resulting graph would be a DAG. On a DAG, we can identify leaf SCCs, and we can traverse from the leaf SCCs to the roots in the bottom-up order. That's what the bottom-up inliner does. It starts with leaf SCCs, and typically these are just leaf functions. Because there is nothing to inline in the leaves, it just runs simplifications on them, and then it moves to their callers. In their callers, it inlines the callees, the ones we just simplified, and then runs simplifications. And it would iterate inlining again if simplifications introduce new calls via the virtualization. And then it moves up to their callers. An important property of this process is in most cases, the bottom-up inliner is looking at fully simplified candidates. Another inliner in the EuroLLVM is module inliner. It is experimental, and it considers all call sides from the module within the same work list. And this can possibly enable heuristics that are not limited by the bottom-up traversal order. We're not taking advantage of this yet, but this is the direction this experiment is headed towards. I described how different inliners traverse the call sides, but I didn't say anything about how they make the decision whether to inline a particular call side or not. This job is delegated to InlineCost analysis. This analysis, given a call side, decides whether it should be inlined or not. And in order to make this decision, it computes two parameters. It computes the cost and the threshold. The cost here is the estimate of the code size increase in case we inline. And the threshold is how much cost we're willing to spend in order to inline this particular call site. Beneficial call sites will have higher threshold and the other way around. And in the end, if the cost is below the threshold, we decide to inline. InlineCost takes the caller context into account, and it tries to predict future simplifications enabled by inlining. For example, here, InlineCost can recognize that bar true is free to inline. As I mentioned earlier, simplifications enabled by inlining is an important effect of inlining, and the ability to recognize them is very powerful. When InlineCost recognizes a particularly beneficial pattern, it gives a bonus to encourage inlining of this call site. The bonus can be given either by increasing the threshold or by decreasing the cost. For example, if InlineCost, looking at the arguments of the call, can recognize that inlining of this call will create a devirtualization opportunity, it gives a bonus. And this feature will be important later in this talk. Now let's see how this all works for us in Falcon. First, let's take a quick look at our compilation model. The compilation unit for us is one Java method. The VM requests a compilation of one method, and then it expects to get the native code for this method in return. The result of the compilation can inline code for other methods, but in order to inline, we first need to request the inline candidate. When we start our compilation, our module contains only one function. This is the function corresponding to the method requested by the VM. And if we want to inline something, we need to request the inlining candidate from the VM. The VM will parse the Java bytecode of the corresponding method. It would generate the LLVM IR, and then we would import this function into our module. And only after that, we will be able to inline. In this model, we don't have full call graph available. Instead, we dynamically explore the call graph of functions reachable from the top level one. And this makes bottom-up inlining problematic. At the same time, top-down traversal is very straightforward. So that's what we did. We implemented a custom downstream top-down inliner. It implements a simple work list style algorithm. We initialize the work list with all call sites in the top-level function. And then for every call site in the work list, we do the following. We request the candidate from the VM. Then we run simplification passes on the candidate in order to clean up after the front end. And then we consider this candidate for inlining using InlineCost analysis. And in case we decide to inline, and in case this inlining introduced new calls into the top-level function, these new calls would be added to the work list. And then the process goes on. We generate, simplify, and then consider for inlining. Once finished, we would run simplifications on the top-level function. And we would repeat inlining after that. And we would continue iterating until we reach the fixed point. We do this because simplifications in the top-level function can open new opportunities for inlining, either by creating a new direct call sites via devirtualization, or by improving information about arguments of some existing calls. This would give InlineCost more caller context, and this way it can recognize more simplifications enabled by inlining. A quick summary. So we've implemented a custom downstream top-down inliner with on-demand generation of candidates and iterative application of inlining and simplifications. Now let's talk about some more advanced features of our inliner. And we'll start with total budget and prioritization. The first issue we ran into while doing top-down inlining is that it's possible to blow up the size of the top-level function. And it happens because InlineCost decisions are local. And iterative application of reasonable local decisions can result in over-inlining. Interesting that it's less of an issue for the bottom-up inliner, because as a bottom-up inliner progresses up the call graph, it inlines into functions, increases their size, and this, in turn, prevents their inlining further up. In order to combat this issue, we introduced the total budget for inlining to the top-level function. But now with total budget, the order of inlining became important. Now we can waste our budget inlining some non-beneficial calls, and we may not be able to inline beneficial calls later. In order to fix this, we need some kind of prioritization on our inlining decisions. And for prioritization, we need a universal measure of inlining goodness. We already have cost computed by InlineCost analysis, but this doesn't seem to be enough for good prioritization. This is because a large Kali can be more beneficial to inline than a small Kali. For example, presented a choice between a large Kali in a hot loop that enables the devirtualization opportunity once inlined, and a small Kali on a cold code path, we should definitely prefer the former. In order to handle situations like this, we introduced an explicit measure of benefits, and we prioritized the call sites by benefit over cost ratio. These benefits are computed by a downstream part of InlineCost analysis, and they are based on InlineCost bonuses. Remember, when InlineCost recognizes a particularly beneficial pattern, it applies a bonus. In our downstream version of InlineCost, we accumulate the bonuses given as the measure of benefit. We've also added multiple new bonuses to recognize Java-specific optimizations, things like devirtualization, subtype check optimization, lock collision, etc. Important to note that there is cost-benefit analysis in LLVM upstream version of InlineCost, but we are not using it here. And in fact, there is no good reason for us to have a separate implementation other than historic reasons. And ideally, we would like to merge our cost-benefit analysis with the one upstream. Now let's see how this translates to performance. Here, I took Renaissance benchmark suite of 25 workloads. I disabled total budget in our inliner, and I measured the impact of this change on the total compile time across 25 workloads and on the scores on these workloads. Disabling total budget increases compile time by about 76%. It also regresses the scores, and the geo-mean impact across 25 workloads is minus 3.1%. This is because as a JIT compiler, we are competing for the CPU resources with the applications. And doing longer compilations, we can hurt application performance. To summarize this part, doing top-down inlining requires total budget for the top-level function. And total budget requires prioritization. We introduced an explicit notion of benefits that is based on InlineCost bonuses. And we prioritize the call sites in our inliner by benefit over cost ratio. Now let's talk about some trade-offs between top-down and bottom-up inlining. Doing pure top-down inlining will lose some of the benefits of bottom-up inlining. As I mentioned before, the bottom-up inliner is looking at fully simplified, fully prepared candidates. This way, it sees more context in the candidates, and it can see more simplification opportunities. This results in lower perceived cost and higher perceived benefit of inlining. And quite often, it's trivial functions like getters, setters, simple wrappers that obscure these kind of opportunities. In this example, if we are looking top-down, we cannot see the constant folding opportunity of inlining bar into foo. But if we're inlining bottom-up, and if we inline baz into bar first, the constant folding opportunity becomes apparent. In order to handle situations like this, we do a limited form of bottom-up inlining. The way we do this is we recursively apply our top-down inliner during simplifications of candidates. Remember, our inliner generates the candidate and then runs simplifications on the candidate. So as part of these simplifications, we would do inlining and we would inline baz into bar in this example. Effectively, we pre-generate two levels of the call graph, and then we run bottom-up inlining on these two levels. This gives us more context in the candidates. It enables more simplifications in the candidates, and it also makes InlineCost able to recognize more simplifications in candidates after inlining. This also collapses the call graph and mitigates the situation where we need to look through several levels of inlining in order to see benefits. When we're inlining into candidates, there is a trade-off. On the one hand, the more we inline, the more context we expose in the candidates. On the other hand, the more we inline, the more we increase the size of the candidate and possibly prevent its inlining. Moreover, if we decide not to inline a candidate, all the work we've done inlining into this candidate, simplifying this candidate, is now just wasted compile time. Our policy for inlining into candidates is we use InlineCost analysis with small threshold of 45. And for the context, the default inline threshold in LLVM is 225. We view this inlining as canonicalization. It's a way for us to get rid of trivial methods like getters, setters, simple wrappers, and things like that. Now let's take a look at performance impact. Again, I took Renaissance benchmark suite, I disabled bottom-up inlining, and I measured the impact on performance and compile time. Disabling bottom-up inlining significantly regresses scores on these benchmarks. And the geomean impact across 25 workloads is about -10%. Disabling bottom-up inlining also decreases compile time about 13%. So doing bottom-up inlining, we have a significant improvement in performance, but it also comes at a steep compile time cost. A quick recap, pure top-down inlining loses some benefits of bottom-up inlining. In order to regain these benefits, we do a limited form of bottom-up inlining. We pre-generate 2 levels of the call graph, and then we do bottom-up inlining on these functions. And this translates to significant performance gains. Now let's talk about the last feature. It is clustering. Sometimes benefits of inlining can only be revealed if multiple call sites are inlined together. In this example, inlining both foo and bar will make the allocation A fully unescaped. This kind of benefits are not recognized by single call site inliner, but they are common enough that we do want to be able to recognize them. And in order to recognize them, we need to consider multiple call sites for inlining together. And we would call it a cluster when we have multiple call sites considered together. And it can be clusters of sibling call sites, or clusters of nested call sites, or it can be a mixture of the two. Because we have total budget for the top-level method, we cannot do cluster inlining outside or after regular inlining. We may run out of budget doing regular inlining, so we may not be able to inline clusters at all. Clusters must be prioritized against regular inlining decisions. So they must be first-class citizens in the regular inliner. So that's what we did. We made our regular inliner work on clusters instead of single call sites. And single call sites in this model are just trivial clusters. In order to make our inliner work on clusters, we need to prioritize clusters. And for that, we need to know their costs and benefits. We compute cluster costs and benefits as aggregate of costs and benefits of the individual call sites contributing to the cluster. Clusters also have some extra benefits. That's the reason why we created the cluster. For example, the benefit of making an allocation fully unescaped. And once we know the cost and benefit of clusters, our priority queue can do its job. And at this point, we can have different clustering heuristics look for candidate clusters. And these heuristics can feed the priority queue. And then the prioritization will take care of the rest. And on every step of the way, we would have the best cluster available for inlining. So far, we have implemented several clustering heuristics. They are all about escape analysis-driven inlining. Essentially, we are looking for clusters that can make allocations fully unescaped, like in the example I showed earlier. So let's take a look at performance impact. Again, Renaissance suite and disabled clustering. If I disable clustering, this regresses the scores, and the geomean impact across 25 workloads is -1.5%. It means that by doing clustering, we are gaining this 1.5%, but it comes at a cost of 3.3% of total compile time. To summarize, some benefits can only be revealed if multiple call sites are inlined together. In order to capture these benefits, we made our inliner work on clusters and not single call sites. And we implemented several escape analysis-driven clustering heuristics. In future, we want to improve our estimation of benefits, both in general and for clusters specifically. We also want to merge our cost-benefit analysis with the one upstream. As I mentioned, there is no good reason for us to have a separate implementation. We want to try different clustering heuristics. We think it's a powerful technique, but so far we are only use it for escape analysis inlining, escape analysis-driven inlining. And we also want to implement cluster merging. In situations where different clustering heuristics identified clusters that have some overlap in call sites, we want to be able to automatically identify merged clusters that capture the benefits of individual clusters at the cost lower than the sum of costs of individual clusters, because there is some overlap on the call sites. And the grand recap: we built a custom downstream inliner in Falcon. It is mostly top-down. It has on-demand generation of candidates, and it has fixed point iteration of inlining and simplifications in the top-level function. It has total budget for inlining into the top-level function, and it prioritizes inlining decisions by benefit over cost ratio. We do a limited form of bottom-up inlining for 2 levels of the call graph, and we also do escape analysis-driven cluster inlining. With that, thank you, everyone, and I'm ready to answer your questions.
All right, here we are. Are there any questions for the speaker?
Thank you. Hi, thank you for the talk. You mentioned you did the bottom-up pre-generation on 2 levels. I guess you tried multiple depths, like 1, 3, 10. So I guess 2 was the best result, the optimal result. But I'm curious if you tried other numbers of depth per generation, and also if you tried on different code base style. You mentioned it works well for simple getters, setters, but if you take a more functional, higher order code base, maybe you would, a bigger number like 3 or 4 or 10 would work better. Have you tried all those different numbers?
Yeah, we did try generation of, so with 2 levels, we have pretty significant compile time cost, but we observed pretty good improvement in performance. We tried doing 3 levels, and at 3 levels, yeah, there are some cases where it is beneficial, but the compile time impact is just too high for this to be practical. And anything beyond that, we didn't see practical examples where we actually need it, and I imagine the compile time cost will be even higher. But for extra level, yeah, sometimes we see cases where we do want to have it by default, but we haven't yet figured how to balance the compile time impact and the quality of inlining there.
Hello, thank you for the talk. Let's say if we are trying to inline a predicated code, so what's your thought about like how the cost-benefit analysis or the budgeting would change with respect to top-down inlining? I just want to hear your thoughts. Thank you.
And can you elaborate what you mean when you say predicated?
So let's say you have the, you're coming top-down, right? So you know the arguments more clearly than you do it bottom-up. So yeah, how can budgeting or the cost-benefit analysis change if you are doing from a top-down inlining?
So yeah, as you said, because we're inlining top-down, we have the most of the context available for us in the top-level function. And we know the most precise type information about the arguments and other things. And the problem we have is with our candidates, because we don't inline as aggressively into the candidates. So we have to do these tricks where we do limited bottom-up in order to expand the context there. But we have full context available for us in the top-level function. I hope this answers your question.
Yeah.
Okay, thank you so much for joining us for Q&A. Appreciate it.
Yeah.